An electric field is invisible to our eyes. Therefore, we need to find a way of visualizing the electric field to show us what the field looks like. Drawing lines to visualize the electric field patterns is a convenient way. We call electric field lines. We know the electric field is a vector with both a magnitude and a direction. Hence, the lines drawn must present the vector nature of electric fields. Correspondingly, the electric field lines have the following properties. Firstly, the electric field vector is tangent to the electric field line at each point. The line has a direction, indicated by a narrow head, that is the same as that of the electric field vector. The direction of the line is that of the force on the positive charge placed in the field. Secondly, let's illustrate the magnitude of the field by the lines. The number of lines per unit area through a surface perpendicular to the line is proportional to the magnitude of the electric field in that region. Therefore, the field lines are close together where the electric field is strong and far apart where the field is weak. For example, this figure shows the density of lines through surface A is greater than through surface B, indicating the magnitude of the electric field is greater on surface A than surface B. We also notice that the lines are the curves, suggesting the directions are different at different locations. To visualize the electric field by drawing the lines properly, some rules for drawing are required. Firstly, the lines must begin on the positive charge and terminate on the negative charge. Secondly, the number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. In the case of an excess of one type of charge, some lines will begin or end infinitely far away. Thirdly, no two field lines can cross. Please note that electric field lines are not material objects. They are employed only as a pictorial representation to provide a quantitative description of the electric field. So only a finite number of lines from each charge can be drawn in space. It doesn't mean that the field is quantized and only exists in the region where the lines are drawn. Actually, the field is continuous, existing every point in space. Next, I will show some typical electric field lines for a field produced by some charge distributions. Firstly, let's see the field lines drawn for a field due to a positive point charge. Because a positive charge placed in this field would be repelled by the positive source charge, the lines are directed radially away from the source charge. In the region near the source charge, the lines are close together, indicating the field is becoming stronger when we move toward the source charge. This figure shows the electric field lines of the field due to a single negative point charge. The pattern is the same as the one due to the positive point charge. The only difference is the direction of the lines. The lines are directed toward the source charge because the positive charge placed in this field would be attracted by the negative source charge. This figure shows us the electric field lines for a field due to 2-point charges of equal magnitude but opposite size, just like an electric dipole. Because the charges are of equal magnitude, the number of lines that begin at the positive charge must equal the number of lines that end at the negative charge. At points very near the charges, the lines are nearly radial, as for a single isolated charge. The high density of lines between the charges indicates a region of strong electric field. Here are the electric field lines for a field of 2 equal positive point charges. The same number of lines begin at each charge because the charges are equal in magnitude. The electric field lies end infinitely far away since no negative charge is available. In the region very far away from the source charges, the field lines are approximately same as those of a single point charge with the magnitude 2q. This figure shows the electric field lines representing the field produced by a positive charge plus 2q and a negative charge minus q. It's found that the number of lines leaving plus 2q is twice the number of lines terminating at minus q. The remaining half lines terminates at infinity. At points so far away from the source charges, the field line pattern is approximately same as those of a single charge of magnitude of plus q. When we mentioned above, the number of lines per unit area through a surface perpendicular to the line is proportional to the magnitude of the electric field in that region. If we put a surface into the field, we could calculate the number of lines penetrating this surface, which we call electric flux. We are going to talk about it in details next lecture.